Hello everyone. I'm Joseph Gallego. I come from the National University of Colombia. My thesis is called Efficient Non-parametric Neural Density Estimation and its application to outlier and anomaly detection. And my advisor is Fourier Gonzalez. So let me introduce a little of the background of my thesis. My thesis is framed in the union of statistics, machine learning, and anomaly detection. There is a really well-known method that calls kernel density estimation method, and we want to overcome their problems with neural density estimation. So, what is density estimation? The idea is to overcome or to estimate a random variable given the data points. So, given a data set, we want to estimate the underlying distribution. So there are mainly two approaches for doing that. There is a parametric approach and a non-parametric approach. And there are several kinds of methods that we can overcome with density estimation and problems like generative models, density estimation, anomaly detection, and classification. So what is kernel density estimation? It's a non-parametric density estimation method. It does not make any particular assumption about the underlying probability density function, and is an unbiased estimator of the probability density function. One of the most known kernel is the Gaussian kernel, and as you can see here, it's only a sum of each point. So it's a memory-based algorithm. So what is the problem of kernel density estimation? It's an inefficient method. It's a memory-based algorithm. It doesn't work really well with high-dimensional data. It's also not differentiable, so we can't integrate with deep learning approaches. And at the end, we have a method that is a memory-based, so their footprint is really high. As you can see in the testing phase, it is constant in terms of the training data points. So there are what are the problem statements? So we want to develop a new novel method that is non-memory based, that is simple, that is good for density estimation, that is also differentiable, and is good for anomaly detection. So for solving this task, we want to introduce the random Fourier features and kernel methods. So as you know, kernel methods, you want to induce a feature space given by a kernel function, and this feature space can be high dimensional or even infinite dimensional. So the problem is the inefficiency of this type of kernel methods. And as you can see there, for instance, if you want to compute the kernel method in a brain matrix, the efficiency is O(n) squared. So one of the ways to overcome this challenge is random Fourier features. So the idea is to give a feature space approximation, and with using that idea, we can overcome the problem with store every training data point in kernel density estimation. These methods come from Rahimi et al. In 2007, and we also provide in our research a novel adaptive Fourier feature that is a further optimization of random Fourier feature using neural networks. So I want to introduce also another part of my thesis, that is density matrices. It comes from quantum mechanics, and density matrices is it provides a way to estimate the probability of a quantum system, and using the Born rule. So with the Born rule, we can produce estimates of a given physical system. It's a more general model of probability. It combines linear algebra and probability, and the clever idea there with density matrices is that it provides probability calculations with linear algebra. What is the problem with density matrices using in machine learning is that making estimate of categorical distribution is obvious, but it's not efficient, it's inefficient. And the problem is how to overcome when we have mixture of non-parametric probability density functions. To overcome that, we propose in my thesis a novel method called density matrices. Kernel density estimation is an efficient approximation version of kernel density estimation. It's also a non-memory based algorithm. It's differentiable and it has two main ways of training: an optimization free and a stochastic gradient descent. So we can combine with other deep learning approaches. And we use a random Fourier feature to approximate the Gaussian kernel and also the density matrices to represent the probability density function. And on the right, you can see our methods. At each point, it is sent to a random Fourier feature. Also, it comes to a normalization, and it provides a density measurement that we call quantum measurement. So the method is based on kernel density estimation. We can derive and change a little bit kernel density estimation so that we can explicitly calculate the density, and using that same approach, using random Fourier feature, we can calculate the density matrices, and using that we avoid the store every training data point. So as you can see here, it is we can use the probability measurement of density matrices using the formula, as you can see here. Making a little change in the equation, we can also use a stochastic gradient approximation, and with that we can further tuning our density estimation. We compare our methods with kernel density estimation, showing that the efficiency of the method is constant and is not related with the training data points. As you can see, another problem that comes with kernel density estimation is that they don't work well with high-dimensional data, and with our novel method, we can overcome that issue. The data set, we also test our method with synthetic data sets, as you can see here, and we show that our methods overcome some of the novel fast kernel density estimation methods, and also compare our method with novel neural density estimation methods, and we show that our method is on a par, or it is compared to other state-of-the-art neural network density estimation methods. So the conclusion is that we can create these methods, and it's a non-memory based algorithm, and we can combine with other deep learning approaches. Also in my thesis, we are developing new methods for anomaly detection methods. An anomaly is an observation that deviates considerably from some concept of normality. Also is known as novelty detection, and it can be solved using supervised, unsupervised, or semi-supervised approaches. The problem with a supervised approach is that typically the number of outliers are low, so we use unsupervised learning approach in that case. There are several kinds of anomaly detection methods in the state of the art, some as shallow, some as deeper work. Our method is framed in the probabilistic frame in the deep neural networks. We provide and test a novel method called anomaly detection using density matrices and kernel density estimation, and it has like 3 steps, as you can see, and we use the method that I was taught in the last slides. We also test our methods. It shows on a part performance or overcome in some cases. This was published in a conference also, and the conclusion is that the novel method showed better performance than a state-of-the-art algorithm. And okay, in contrast with kernel density estimation, this novel method doesn't have huge memory requirements. The last part of my thesis is streaming anomaly detection. This was a work presented in ICDM conference. The idea here in streaming anomaly detection is that the data arrives continuously in large quantities, so it's impossible to store every single data point. So our idea is to develop a novel streaming anomaly detection method using the same ideas with density estimation. And the problem here is that the patterns evolve with time, so it's really difficult to know at the beginning what is going to be the anomalies. The streaming anomaly detection method, there are several. Also, one come from the shallow methods, another from deep ones. We compare with the state-of-the-art like Kitsune, NStream, and MNStream. And the idea is this one. We want to, for instance, we have a time series, and the idea here is to provide a density estimation, as you can see below, and our methods. The idea is that it estimates less probability to anomaly data points. So the problem was how KDE can be adapted in such a way that it can perform efficient anomaly detection on streaming data points. So we come from Inc math that follow the same idea using adaptive Fourier features, and it can be updated with each new data point. See, if the new data point is not an anomaly and is classified as a normal data point, this data point we use as an updated data point for the density matrices. And we compare also our method with several data sets and to other state-of-the-art streaming anomaly detection methods, and we show that our methods perform on a par or in some cases over from other anomaly detection methods. So the conclusion is that in-math show better performance than state-of-the-art algorithms. It computes density estimation, giving an anomaly measure for each point. And okay, what is next? Right now we are developing a novel method to also to anomaly detection and density matrices. It comes from some similar ideas that I am presenting right now, and it's the idea that I'm going to develop this year. So thank you very much. This is the QR for the paper that are presented right now.
Yes. Thank you, Joseph. So I have some comments that are mostly not technical, and I think that probably most of the student presenters, it will be applicable probably to many student presenters. So first with some of the things that I liked. I liked in the beginning that you had a slide dedicated to applications. I think it's really important to, we have a wide range of expertise in this room, and so it's really great to have something that people who are not in your area can, ground their understanding to and say, okay, this is going to be useful for anomaly detection. I don't work with, density estimation, but I can relate to that. And then you identified very early on what the problems were with the existing methods. They are inefficient, they can't deal with high-dimensional data, and I think there was another thing. But I thought that that was really good. It set up the problem well, and it gives the audience an idea that this is something that's important that you're working on. You also had something that looked kind of like a product description with like the different features of other approaches and the ideal, and had all the checkmarks, and I like that as well. I think that overall the presentation was maybe at a level too detailed for a broad audience. It's clear that you have really strong technical depth, and this is very interesting work. But at points, although visually nice looking, the slides were going very fast. And so, there were many results tables where I could see quickly, this is the bar that corresponds to your method. It's, the error bars are higher, but I didn't know what the F score was referring to, and it's very easy to get lost in those details. In general, we have a limited cognitive capacity, and so I think there's different styles. Some people think that the slides should stand on their own, or the slides have to complement what you're seeing, or what you're saying, but it's very hard for the audience to fully absorb the words you're saying and just what's visually being shown, and get the whole thing, especially if it's going too quickly. I think that the speed was sort of one thing that got me confused and got me lost. I think that you had another positive thing is you had a clear structure that corresponded to individual pieces of work in your thesis. And you went back to that, which was good, but the speed kind of, it was difficult to keep up. Another piece of information that I got from your statement, independent from this presentation, is you have a strong publication record. And I think maybe using those individual pieces of work as a way to structure your presentation in the future might work well. I think that's kind of what you were going for, but with a little bit of a slower pace and a little bit more on the high level, I think it would be a bit stronger. But overall, I think you're doing great work, and thank you. If anybody has a specific comment, other specific comments or technical questions, it would be good to discuss.
Thank you so much for your presentation. I would like to know what's the difference of using kernel or using other non-parametric estimators that can be, for example, feed forward.
What is the difference?
Yeah, why do you think kernel estimation has a value on top of other non-parametric estimation methods? Like it could be, for example, I can use a feed forward.
There is a trend right now. The problem with neural networks, you can estimate whatever you want with a density with a neural network. Yeah, but maybe there are like a mathematical foundation in kernel methods that is not so obvious in neural networks. It's difficult to overcome that, and for me, it's easier to because there are like maybe there are more mathematical strong related with kernel methods that is not, for instance, in neural networks. Besides that, I think that in more traditional statistics, for instance, if you want to use maybe a mixture of Gaussians or something like that, it will be really difficult to tackle the novel problems with big data, and it's really difficult to do doing that. In the case of neural networks, right now there are neural networks for density estimation, but I don't know, this maybe is a different path to go. Yeah, because right now it's like everyone's want to go to neural density estimation methods, and maybe this is another way to look at.
Thank you.
Any other questions or comments? I have some small comments on your presentation. Overall, it's a great presentation. I think you made this customer HTML. I find the fonts are really small. I'm sitting the first row. I'm not sure if people in the back they can see that. Especially I remember you have one slide with all the bar. I can see the bar. First, those colors are quite similar. It's really difficult to distinguish them. And also the text below the bar, I really can't see what's going on there. I don't know what you are referring to. So one suggestion I always give to students is make sure your font is I don't know how to gauge on this HTML page on PowerPoint. Usually it should be larger than 24 or 28 points.
Yeah, actually, it becomes an accessibility issue actually, and there's tools out there also for picking colors that people who have certain color blindness can distinguish. But yeah, I think that those kind of tools should be more commonplace now.
Any other comment? Question? If not, let's thank our speaker.